Kindly please allow me to go through some house rules first before we start. This session is accredited for 1 CPD point for HPCSA and South African Nursing Council registered participants. Nursing Council colleagues will need to contact Leboham for directions on how to upload their CPD points. Kindly please drop your HPCSA number, full names, and email address in the chat box to register for CPDs. For those who are not registered with HPCSA or South African Nursing Council, an attendance certificate will be issued to demonstrate your growing knowledge capacity in areas covered by our platform. Please keep yourself muted at all times to avoid interrupting the presenter. Disruptive attendees will be removed from the webinar and will not be able to join again. The session's attendance will be monitored for its entire duration to ensure full attendance. Kindly please ensure that you do not join using nicknames or handset device names to be properly identified and allocated your points. Each session will be podcasted on YouTube for long-term education and training purposes. We have realized that a lot of colleagues go back to our YouTube page to recap on the information that may have been missed during our sessions. We also urge you to post your questions on the video platform to continue empowering colleagues who will always be able to access our learning material. The link that you have used to join this session is a recurring link and can be used every month until the end of the year. I believe we still have one last session left. Participants will be allowed to ask questions or comments after the session. Questions can be posted in the chat box as well anytime during or after the presentation. Our sessions are multidisciplinary in nature and meant to empower colleagues from different professional backgrounds. Kindly please be patient during moments when we discuss topics that may not be relevant to you but others. Colleagues, please sit back and relax. The webinar is about to start. Today marks our very first occupational health and environmental health research report sessions that emphasize on measurements of small dust particles that happen to be very toxic and often go undetected because the focus is often on larger particles that are often less toxic compared to the smaller particles. On the 15th of November, we will host the part 2 of the risk assessment refresher that we hosted last week on Saturday. This will be played on Zoom. The Zoom link will be provided between 9 o'clock and 12 o'clock. Or for those who had attended last week, we will be using the same Zoom link that we used last week. On the 27th of November, we will be discussing ethical aspects of occupational health at 6 p.m. during our regular monthly slot on Zoom. This session will be accredited for ethics CPD points. We look forward to you joining us in these two important sessions. South Africa is counted amongst countries with highest prevalence of silicosis due to its rich mining background. However, the focus of the government and the other legislative agencies is mostly concentrated on gold and platinum mining sectors, with less attention on the other industries that have been reported to contribute significantly to the high statistics of silicosis worldwide. These industries include surface mining, also known as open pit mining, quarrying, and granite and stone cutting operations, and they have individually reported to contribute significantly to the silicosis statistics in the literature. In today's session, we focus mostly on dust emissions in the stone quarrying sector and the effectiveness of one of their dust control strategies with specific focus to smaller particles that are below a micrometer in diameter. To make more sense, we introduced our research report by defining the following key terms. The first key term is particulate matter. Particulate matter is microscopic solids or liquid droplets that are so small that they can be inhaled and cause serious health problems. The second term is fine particulate matter, which is particulate matter that contains microscopic solids or liquid droplets that are so small that they can be inhaled and cause serious health problems. Fine particulate matter refers to particles that are smaller than 2.5 microns in diameter. 2.5 micron is also 2.5 micrometer in diameter. 1 micrometer is 1,000th of a millimeter. So if you take 1 millimeter and divide it by 1,000, you get a micrometer. That's how small we are talking today. Submicron particles is the portion of particulate matter that is less than 1 micrometer in diameter. And today's session focuses particularly on submicron particles. And then we have what we call ultrafine particles, which is a portion of particulate matter that is smaller than 0.3 microns or 300 nanometers. So colleagues, you know when people are talking about nanoparticles, we are now talking a fraction of a micron. So when we say 300 nanometers, we are referring to 0.3 micrometers, which is also known as 0.3 microns. Total suspended particles refers to all airborne or suspended particles in different sizes, mass concentration, and number concentration. And then there is a concept of deposition, which refers to the process by which dust particles are laid down on the ground after emission from the source. So when dust is emitted from the source, the process by which these particles will fall is called deposition. And as we know, bigger particles will deposit around the source and smaller particles will deposit a bit further due to their light weight and their ability to be carried by wind. This may occur immediately following emission or after transportation by wind. Resuspension is the process by which deposited dust or particulate matter are reintroduced into the atmosphere after being physically agitated or lifted up by air. So resuspension means dust particles that had fallen on the ground and then there is wind or any other force that lifts them up and make them airborne again. Colleagues, today we are presenting research titled Efficacy of Water Suppression Against Submicron Particle Emissions at a Quarry in Ekurhuleni, South Africa, which is a multi-phase comparative study. This research was conducted by myself, Dr. David Mkwanazi, together with Dr. Daniel Masekameni, who is now Professor Masekameni, currently based at University of South Africa. But at the time of research, we were both representing the School of Public Health at Wits University under the Occupational Health Division. Previously, work-related respiratory diseases used to constitute up to 60% of all diseases and injury mortality for decades, and over 70% of occupational diseases, mortality worldwide in all industrial sectors. Currently, this accounts for about 6.1%. So we have moved from 70% to 6.1%. So the mortality, 6.1% of the mortality that we are having now is due to occupational health reasons. And this is according to World Health Organization. And then the poor outdoor and indoor quality has led to over 7 million premature deaths. And according to International Labour Organization, back in about 2021-2022, the number of deaths that were caused by these occupational diseases relating to poor indoor quality per day were about 2.2 million, and the number is now standing at 2.7 million, translating to one person dying every 15 seconds or so because of work-related matters. And then quarrying and stone crushing are responsible for different workplace hazards, and this usually involve physical trauma from either interaction of human beings with these rocks themselves or vehicles or machinery that is being used at these quarries, chemical hazards, primarily dust, vibration, noise, ergonomics, and under chemical hazards, the main culprit is silica, respirable silica dust. So, also known as RCS, respirable crystalline silica. This is what we are here about, colleagues, about the exposure to silica that people who work in quarrying and open pit mining are exposed to. And then we further say that the toxicity of particulate matter is influenced by different characteristics. The first one is the diameter of the dust particle. Like we said, larger dust particles are very heavy and tend to fall down or get deposited around the source, meaning usually smaller particles are able to travel further compared to the larger particles. Chemical composition of the dust particles, in this case, particles that contain silica or other toxic chemicals are more toxic than an ordinary particle. And the internal dose refers to the amount of exposure that results from the dosage that is introduced to an employee. How much is uptook by the employee of this dust? So the larger the dose, the more toxic it becomes. And then there are different dose matrices that are used in singular forms, dose metrics that are used to estimate emission concentration at various workplaces. The one that is commonly used by various legislative authorities, including our government, is milligram per cubic meter. However, this unit usually represents the mass concentration. And the disadvantage about this is that it only becomes more accurate or more reliable for particles that are larger in size, because the larger the particle, the heavier it is. So if we are going to talk about mass, obviously larger particles will weigh more. So you'll be able to weigh them more effectively because they are heavier. Smaller particles will weigh way less. However, their number will be much higher because of the light weight and the concentration due to the large number of these particles. So deposition of particulate matter in human lungs depends on its surface characteristics, such as the aerodynamic size and the weight. Again, when we refer back to the statement that we made about deposition, larger particles tend to fall around the source. So meaning if you are standing 100 meters from where the source of the dust is, the particles that are likely to reach you are smaller particles which are light in weight and are able to get carried away by wind, compared to bigger particles that will usually just fall around the source. So similarly, what ends up in the human lungs depends on these characteristics, their ability to get airborne, which is what we call the aerodynamic properties, and their weight. Heavier particles will quickly fall down and will not fly far or will not be transported by wind further than where they originated from. But lighter particles will end up where the human being is, in this case, where the employee is, with the potential of being inhaled and ending up in the lungs. I introduce you to this picture, colleague, which demonstrates that particles that are larger than 5 microns or 5 micrometers will usually be trapped in the upper airways. Again, this is because the human lungs or human respiratory system has the embedded mechanical system that is designed to eliminate dust particles that end up in the lung cavity or in the respiratory cavity. So the human apparatus or the human abilities that we have, that we're equipped with to eliminate dust from our lungs, are usually very effective against dust particles of this size. And then we go to smaller particles that we said are fine particles or fine particulate matter with the size between 1 to 5 microns. As you can see in this case, let's go back. As you can see, in this case, they end up in deep in the lungs. So they get deposited inside the lungs. Again, the term deposition resurfaces. So instead of being deposited near the source or outside the human environment, because of their size and the light weight, they end up being deposited in the human lungs. However, we then look at a smaller size of particles, smaller than 1 micron, which we now call submicron particles, which is what this research was about, which now end up in the pulmonary alveoli through diffusion. So it means now these smaller particles are able to chemically interact with your lung tissue to end up in your lungs and be able to cause disease. And then we have smaller particles of about half micron, which get phagocytosed by the alveolar macrophages or the cells in your alveoli, which are now even more dangerous because of the type of interaction they have with your lungs. So the problem with this is that government agencies tend to focus on the dust particles between 1 and 5 micrometers when they set regulations and when they enforce regulations. And they usually don't focus on particles that are smaller than 1 micron. And the biggest problem with this is, additionally, is the fact that some of the machinery or equipment or tools that we use to measure dust particles usually only focus on 1 micron up, and some of them, most of them, do not focus on particles that are smaller than 1 micron, which is why we were interested in particles that are smaller than 1 micron. Furthermore, colleagues, it has been proven that water suppression is able to control dust in the mining and construction industries. So by spraying water onto dust, you are able to control some of these particles. However, most of the studies have proven that this is more effective against larger particles instead of smaller particles. So typically your PM10 or 10 micron particles and slightly smaller than that, this is where most of the studies have concentrated their efforts on. And particles in this size range, however, are not most commonly associated with the development of respiratory disease, because remember we said bigger particles usually get eliminated by the lungs' own defense mechanism. So when you cough up the dust or the sputum or the phlegm, usually you eliminate this type of particles or this size of dust particles. So the ones that the government and researchers tend to focus on are not really that problematic because they usually end up outside the human body anyway. However, compared to the smaller particulate matter, PM 2.5 or particles measuring 2.5 microns or submicron particles, these are not very effective, suggesting that water suppression may not be an effective means of preventing and controlling emissions of submicron particles. And this is what we based our research on. To evaluate the efficacy of water suppression in reducing PM1 particles. PM1 is the same as submicron or particles at least at 1 micron size. During different stone crushing phases, the use of a tool that could effectively measure emissions under typical or simulated human exposure conditions was important. So it was important for us to conduct this research without exposing any human beings by simulating typical human exposure conditions, meaning in terms of the height and where a human being was likely to pass around the quarry. This was a multi-phase comparative analytical cross-sectional study. A study of this nature usually just measures how much exposure there is. Doesn't focus on why and what causes what. It just focuses on how much. And this was in the occupational setting in a dolerite stone crushing quarry in Ekurhuleni, South Africa. Dolerite is a type of stone that contains at least 50% of silica or respirable crystalline silica in the stone. So 50% of this stone is actually silica. This stone is usually used in the construction and railway industry to make concrete, the concrete that we build with and that we normally find around the railways originates from this type of stone. Data was collected in early October under typical weather conditions, so it was very important for us to make sure that this is not influenced by wind or any other conditions that might have contaminated the results. Samples were collected at 4 different sites, and we're about to elaborate a little bit more on that. There's an area that they call primary area, where very large rocks that have been mined are crushed into 150 millimeter stones. So they take those big rocks, load them through with front loaders into a jaw crusher, and the jaw crusher will break the stones into 15 centimeter or 150 millimeter stones, meaning much smaller stones. And then from there, these stones will be conveyed to the secondary area, which has a 57 millimeter screen. 57 millimeter is about 5.7 centimeters. We are now talking smaller stones, almost the size of a golf ball. And at this station, secondary area, there is a water suppression function that is embedded into the system or into the stone milling machine. So, meaning the stones, as they pass through a certain point, they get sprayed on with water to reduce the dust content. So, this was in our study classified as a wet area. The primary area, because it's dry, dust comes as it is, and there's no mechanism to abate dust at all, is considered a dry area. So in our study, we're comparing dry and wet areas. And then there's a tertiary area with a smaller screen. A screen is a sieve onto which these stones are pressed and then broken into smaller particles. And then you get to have smaller stones. And then you'll notice that 1.9 centimeter is the same as 19 millimeter, which means at tertiary area, we are now talking about a concrete size stone. So it means our stones have now been broken into concrete pieces that we normally see on the roads or at the building sites where the construction takes place. And at this stage, there is a huge water bath or water tank filled with water where the stones are dumped into. And obviously, this is for the purpose of washing the stone because we are now going to process the stones further into smaller particles, 5 millimeter, 2 millimeter, and sand-sized particles. Sand is also generated in the same plant, but we were more interested in these three sites in addition to the fourth site or sampling site, which was the office block where everybody sits, the manager, the general workers. There was even a cat or two and plants, which is about 200 meters away from the plant or from the jaw crusher. So there is, as mentioned, there is human and animal and plant activity there. So we wanted to see how much dust actually does get to the office block. Okay. Let me see if we still have our laser pointer. Okay. All right. So on the right half of the picture, the right side of the picture, we are looking at the here exactly where the laser pointer is. This is where the jaw crusher is. So trucks will come from the mining area somewhere, front loaders, I mean, dump those big rocks onto this crusher. And they will get crushed into 150 millimeter size, which will now be conveyed. This is a conveyor that conveys this onto this huge stockpile here. And then there is a smaller stockpile. So smaller rocks, because obviously when you break rocks, it's not guaranteed that you'll get the same size. You will get smaller sizes and bigger rocks. So the 150 millimeter rocks are dumped here and smaller rocks will be dumped this side. That's why you see two conveyors. And then from here to here, there is an underground conveyor that takes these rocks, convey them all the way to the secondary area. So this is the secondary area and this is the tertiary area. So our first sampling point was here where you see number 1, where dust is emitted from this huge stockpile as it gets loaded onto the conveyor belt that takes it to 2. There is no water suppression here, so it was considered a dry area. A secondary area has a sprinkler system inside this housing, which sprays these rocks to minimize dust. So it was considered a wet area. This is where the stones are now 57 millimeter. And then tertiary area from there, the rocks will be delivered to the tertiary area, dumped into this bath full of water for rinsing. And these rocks are now 19 millimeter in size. And this is the tertiary area. And then where you see number 4, that's where the office block is. The distance between here and there is about 200 meters. 2 soccer fields. You know, if you consider the length of a soccer field, about 2 soccer fields. So we placed the 4th sampler here to make sure that we can measure exactly how much dust is able to move from where the activity is to where the human beings are. That was the main reason for including the sampling point number 4. The machine that we used is called NanoZen Dust Count 9000. Very expensive, I assume. It's a personal dust sampler that is usually attached to human beings who are exposed to dust. But in this case, we had to be creative and put it there by itself because we didn't want to expose any human being. Cover it under a hard head, like a wrapper in normal South African language, because there are rocks flying all over the place to make sure the rocks don't crush the machine itself. And then there is a piping probe that was extended to where the dust was. And this was at the height of about 1.5 meters, assuming the normal. Remember, initially we said this was a simulated environment. So simulating at about 1.5 meters high, which is the breathing area for a normal or an average human being. This is through a Teflon tube. Teflon is just the material of this tube, which was 1 meter long. And then inside the machine, there was a 37 millimeter cassette with a 2.5 PM 2.5 cyclone, which counts these dust particles to make sure that we get the particle sizes we are looking for. So this was able to monitor the emissions. Yeah, this was able to monitor the emissions between 0.3 micrometers or 0.3 microns to 10 microns across these 4 different sizes. But remember, we're only interested in less than 1 micron. I've mentioned it was positioned at about the height of 1.5 meters at all the sampling points, and every sample was taken over an hour to determine how much dust is emitted in 1 hour. And then we were able to measure dust in real time. I'll show you the graphs. The instrument limitations is that the instrument cannot differentiate between the particles and aerosols. Particles are solid. Aerosols may involve or contain anything, including liquids or micro droplets of liquid. And this is the picture of the sampler that we were using. You can see it's a very small machine. It's about 13 centimeter by 9 by 4. So this is a pocket-sized meter that you can actually fit in your pocket, or that you normally, under normal circumstances, it's hooked onto your overalls, and then the tube is connected here on the mouthpiece, and the end of this tube will be somewhere around your breathing area to calculate exactly how much dust reaches your respiratory zone as an employee. So like I said, we measured the dry areas, which were primary and the office area, number 1 and number 4, and then the wet areas, which was number 2 and number 3. And then we compared all the 4 areas that were used as sampling points. Data were analyzed based on mass and number concentration. You'll remember I said, according to South African standards, this data is measured according to mass concentration in milligrams per cubic meter. And then there is a number concentration also in different sizes under wet and dry conditions. And then we used Microsoft Excel to analyze this data. The results that we obtained, the primary area where those large stones are dumped and carried by an underground conveyor, gave us 460.2 micrograms. Sorry, I said milligrams earlier, but it's micrograms. 460.2 micrograms per square meter. This is very high, colleagues. Remember, the occupational exposure limit for South African industries for respirable dust is 5 to 10 micrograms. No, 5 to 10 milligrams per cubic meter. So this was 460 microgram per cubic meter. Smaller than that, but remember, this is just over an hour. So you can imagine a person who is exposed under these circumstances over 8 hours. If you multiply that number by 8 hours, you'll get an idea how close it gets to milligrams. Remember, this is micrograms. Let me just quickly glance at my calculator to make it more practical. So it's 460.2 multiplied by 8. So we are looking at 3.6 milligrams. Yeah, 3.6 or almost 4 milligrams per cubic meter. Almost close to the limit of 5 milligrams per cubic meter, which we are not supposed to jump. And obviously on certain areas, the dust will be higher. And an average number concentration was 222 million particles per cubic centimeter. We are now talking centimeters. When it comes to the number concentration, remember we said government agencies usually use mass concentration. But if you had to literally calculate the dust particles, this site was emitting 222 million dust particles per cubic centimeter. If you draw 4 lines, 1 centimeters each, a square of 1 centimeter, the cubic centimeter, in that small cubic centimeter volume, we have 222 million. We're not even talking cubic meter, which is much bigger than that. And then, so this was the first sampling point. On the second sampling point, colleagues, I'm trying to make science easy to understand here. Please forgive me if I sound too technical. This was a very technical study, an occupational hygiene nature of a study, but we are translating it as an occupational health study. So on the second sampling site at number 2, that 460.2 was now reduced to 6.0 micrograms. And that 222 million was now reduced to 60.9 million, which is much less than the original concentration. So at site 1, very high, site 2, much better. Site 3, the mass concentration, the weight of this dust emission, unfortunately, it increased to 10.5 compared to 6.2 at number 2. We are now at number 3. But the number concentration went down to 54.8 million. What does this say? It simply says we have a less or a lower number of particles which are much heavier than what we had in number 2. And I can tell you the reason why the weight was higher at number 2 compared to the weight was much higher at number 3 compared to number 2, because we were expecting for it to be much lower. But it was higher because we are now measuring dust particles that have been immersed in a water pool. So meaning as particles leave that water bath, they are now bigger and they weigh heavier because of the attachment to water molecules. So it means our numbers at number 3 were not very reliable because there was a confounder in the form of water particles that were now attached to these dust particles, making them heavier than they were when they were dry at number 2. I hope that's simple, colleagues. So the number of particles is lower, as you can see, which is now 54.8 from 60.9, which means there is a reduction in terms of number. However, the few particles that we found at number 3 are now heavier because of their interaction with water. And then when we go to the office block, look at number 2. Number 2 was 6.02. The office block concentration of dust was 6.07. More or less the same, but slightly higher. But that's in terms of mass concentration. But in terms of number concentration, it was again way less than number 2 and number 3 at 44 million cubic centimeters. So now again, if you look at this number at number 4 compared to number 2, it means in terms of mass concentration, the dust levels are more or less the same. Meaning whatever you are trying to do to prevent dust exposure at the secondary production area doesn't really make a lot of difference when you are at the office block, because you are still breathing or inhaling exactly the same concentration of dust as if you were at number 2. And number three, we did mention that it's confounded by water particles, which does happen in research. Sometimes we encounter things we didn't anticipate. So, but in terms of number particles, number concentration, we now have 44 million, which is less than the 60.9 million at number two, which tells us that the dust at number four is the particles are much larger than what we got at number two. All right. This is the mass concentration graph, colleagues. Looks like gibberish. When I was busy with this study, it made so much sense to me, but yeah, at this point, I'll try my best. So you can see the graphs. Blue is the primary area. So the high emissions that we obtained at primary area compared to secondary, tertiary, and office. You see this line here at the bottom, close to zero. These were the emissions at the secondary, tertiary, and office compared to the large amount that was released at primary area. So you can see already that there is a huge reduction in terms of mass concentration. But you'll remember we said mass concentration is not really that reliable, especially when you're dealing with smaller particles. I'll show you why at the later stage. We're now looking at the number concentration. The graph shows you already. You are now starting to see the secondary graph, tertiary, and the office graph, which means on simple face value, the reduction is not so much in terms of number concentration compared to mass concentration. With mass concentration, these levels that we are looking at here were somewhere here around zero. But now you can see they are starting to raise their heads a little bit. With number two relatively higher than number three and number four. Number four, you can see in terms of number is very low. So remember I said the numbers I gave you were the average concentrations over a period of an hour. Right. So this table just shows us the reduction effect from primary to office or from number one to number four. In terms of mass concentration, if we start here, from the original 460.2 to this dust was reduced by 99%, meaning we were only left with 1%. But from 460 to this was only reduced by, at the tertiary level, at number three, it was only reduced by about 56.7%. And then at number four, the office, at about 99%. And this is a 76-fold reduction. At number two, reduction of about 43 times at number three, or reduced to about 75 times less than what it originally was at number four. If you look at the number concentration, and you can easily compare the reduction in number concentration and the reduction in mass concentration. In the number concentration column, the reduction between primary and secondary was only 73% compared to the 99%, which means the reduction is mostly in terms of the weight, but not the numbers. The effect was much less on the numbers. Tertiary, it was about 75 in terms of numbers, and office block, which is number four, the reduction was about 80%, which is 5 times less than the original amount of 222 million. At tertiary, it was about 4 times less. And at secondary level, number two was about 3.6 times less. Trying to fake simple mathematics out of a complicated scenario, colleagues. This is just a comparison of total emissions across the four sites. In terms of numerical values, you can see the weight was 460.2, which is very much high. And look at the weight at secondary. Tertiary, we did say because of water, it was much heavier. And then at the office, it was slightly higher than that, but we attributed that to the wind blowing dust from the original source to the office area. So as you can see, you can literally not compare number two, number three, and number four, except when you are talking about the number concentration, because the reduction is only about 80% and 70 to 80% compared to 99% on the other hand. So we are now focusing on the small particles smaller than 1 micron, meaning we have dumped the load between 1 to 10 microns. We are now focusing on the values smaller than micron, smaller than 1 micron or 1 micrometer. You can see at primary, in terms of the number concentration, sorry, it's supposed to say number per cubic centimeter, not cubic meter. The value there was 21, no, yeah, 21, 21.6 million particles per cubic centimeter. And then here we were looking at 984,000. There we were looking at 865,000. And then at number 4, the office, we were looking at 713,000. So that's when we dump the load of those big particles and only focus on the small particles smaller than 1 micron. I hope it makes sense, colleagues. So from 220 something million, we are now left with 21.6 million. And then on the secondary area, we're looking at 984, 865,000, and 713, which is still a lot. Imagine counting 984, almost a million particles within a centimeter block. Not even a meter block. It's still a very high concentration. Right. The next slide shows us the breakdown of different particle sizes under 1 micron. So at 0.3 micrometer or 300 nanometers, we almost found nothing, but there was a very small amount there. This speaks to the limitation of our machine. Our machine is only effective from 0.375. So meaning there could still be a lot that we are missing out on, especially in terms of dust particles that are smaller than 0.375. So you can see the smaller the particles, the larger the number. We have now dumped mass concentration altogether because we have seen that when it comes to smaller particles, it doesn't have that much effect. So we are now focusing on the number concentration. You can see at this particle size between primary, secondary, tertiary, and office, look at how small the reduction is from there to here to here to there. But as you grow the size of particles, the effect starts becoming more significant. Look at the gap there, much larger than there, much larger here, even larger there. And there it's because there weren't so much of those particles at that size, almost 1 micron. This is 9.15 or 915 nanometers. So we are now talking nanoparticles, the particle sizes or diameters. So you can see from this picture that the reduction became better and better and better as the particles grew in size, meaning smaller particles did not really show that much effect of water suppression, but the larger the particles, the more the effect we can observe. And then in our discussion, we concluded that there was a significant reduction between dry and wet areas. 98% reduction on average between dry areas. And in terms of mass concentration between dry and wet, and 72.5 in terms of number concentration. Remember, colleagues, we said there wasn't that much effect in terms of number concentration, which is why one of our recommendations was that government should start focusing as number concentration as a matrix compared to the mass concentration. There was a substantial residual dust exposure around the office block, possibly due to wind, because a major portion of that dust was mostly large particles, which were heavier. Remember, we said smaller particles are lighter, and we see them more under number concentration and not mass concentration that much. So, because the mass concentration was higher at number 4 compared to number 2, we can conclude that there were bigger particle sizes that were probably carried there by wind. And then the third point was that water suppression was highly effective against particles that were larger than 1 micron. I've shown you on the graphs, with a much poorer effect on smaller submicron particles. So it was not as much effective as it was on smaller particles compared to larger particles. In fact, you could see on one of the images that the larger the particles became, the more effective it became. More data is required on submicron emissions suppression. We are not doing much to determine the effect of these particle sizes on human beings. We are mostly focusing on bigger particles, which are not really that much dangerous compared to this group or compared to this bin size that we are not focusing on. Consideration of number concentration is recommended as a key dose matrix to determine the exposure compared to mass concentration. The predominance of PM or particulate matter around the office demonstrate that normal quarry controls mechanisms were inefficient, meaning dust was still able to reach people at the offices. Remember, at the offices, people don't even wear masks because they consider it a safe environment without dust exposure. Small particles appear to remain in the air for much longer, where the dispersion and movement could be influenced by wind and speed, as demonstrated in literature. So this was consistent with what literature says. And then resuspension of deposited large particles from nearby stockpiles of the ground could be possible for precipitation of large bin sizes, PM4, meaning 4 micron to 10 microns in the office block. This is what accounted for the larger mass concentration. The available dust control legislation does not target this PM size range despite its health effects. So you're more likely to get silicosis from these small particles than large particles, because the large particles don't end up in your lungs in any case. What ends up in your lungs is these small particles. And our conclusion was that the sampling tool that we're using was able to meet the objectives of the study. It demonstrated capabilities of personal dust samplers to measure submicron particles. While we're still waiting for somebody to develop sophisticated equipment that can measure these very small particles, we can use these small dust samplers effectively, except for when we are interested in particles less than let's say 300 nanometers, because we could see at that level we couldn't find anything. Not that there was no dust in that level, there was, but it was just beyond the capabilities of the machine. And then we could potentially fill the gap of sampling equipment using these tools. We could also potentially motivate for focus of impact on submicron particles on human health and influence the exposure control mechanisms. If we want to control exposure, we also need to focus on these smaller particles. Like we've said, we were only able to measure 300 nanometers and larger sizes compared to that. Recommendations: access to high dust emission areas should be prohibited due to the risk of physical injuries from rocks and other effects. Restriction of access to only control rooms to avoid dust exposure. Administration area should be regarded as a high dust exposure area also. You could see how much dust was there. It was almost similar to number 2. Occupational hygiene surveys performed around the plants must include submicron particles. and medical surveillance programs must be aimed at addressing potential exposure to ultra-fine particles and fine particulate matter sizes. Controls that are in place must also be adapted to cater for small exposure to smaller particles. And policies must be amended to highlight the risk and controls of occupational exposure to fine particulate matter. Colleagues, are there questions? It's exactly 7 p.m. We have a few minutes for questions before we conclude, if we are still awake. I'm just quickly checking the chat room. Are there no questions, colleagues? All right. Like I've said, colleagues, as part of occupational health, we need to distribute our subjects evenly and fairly to cover subjects such as research as well. So I thought today's session should be on one of the studies that I had done. This is a study that I presented 2 weeks ago at the South African Occupational Hygiene Society conference in Durban. And I thought you would find it interesting to discuss this. And I see Dr. Kumalo is there. I've noted you, Dr. Mkwena. And yeah, I just want to see if thanks for sharing this great study. This is Dr. Ngoyama from PE and iPhone 2. Does milk have a role to play in dust suppression in the lungs? That's a big no, colleagues. It's just a belief that most dust exposed workers have. And I know plasterers in the construction industry also believe that there is an effect. Dr. Mkwena, may I please ask you to unmute yourself and ask the question?
Thank you so much. Can you hear me?
Yes, I can hear you, Doc.
No, thank you so much, Dr. Mkonazi. Really appreciated. Very beautiful study, and we must congratulate you for the really this bravery to conduct such a, I think, as you said, occupational hygienic inclined. I think it's very good for us.
Yes.
Maybe just few questions that I'm very curious about. Looking at you were able to explain the concentration between the primary and the secondary. I'm just curious with the office, looking at the distance that you showed. I'm not sure how far it really is. That the concentration was still not so much different in comparison. What would that be the reason? I think you explained very nicely to us why the secondary was still high. So I'm just curious in relation to the office space. The other question that I wanted to find out, we always talk about research for action. Was this discussed and shared with the place, the colleague or the company? And lastly, what were the measures in place looking at some of the things that you have uncovered? Thank you so much.
Thank you very much, Doc. Yes, to start with number 2 and number 3, the findings were discussed with the safety officer and the plant manager, and a formal report was drafted for them to discuss with the management of the quarry. The quarry belongs to one of the biggest cement manufacturers in our country, so they take health and safety of the employees very seriously. In terms of the first question, very interesting question, Doc, because if you look at the concentration at number 2, it's in terms of mass concentration, it's 6.02. And then at number 4, it's 6.07. Numerically or statistically, more or less the same, but the composition is different in terms of weight or the mass of the dust particles. We were able to determine this by looking at the number concentration. At number 4, you have the same mass concentration, but with less numbers, meaning fewer particles weighing more or less the same as particles at number 2. This could only mean one thing. Although we're not interested in how the dust got from number 2 to number 4, but we could make a conclusion that the dust at number 4 was mostly bigger particles that were probably carried by wind. Because remember, number 4 is just an office block and there are no dust emissions coming from that side. But if you look at the number concentration, the numbers are much less. I think it's 44 million compared to 60 million. That's a huge reduction numerically. But in terms of weight, it's more or less the same, meaning the major load of this 44 million at number 4 is accounted for by much heavier particles. And we know from literature that particles that are heavy in terms of mass are also larger in terms of size. So the distance between the two is about 200 meters, the length of 2 soccer fields, strategically placed there to make sure it's far away from the dust source. But again, we've demonstrated that some dust particles are still able to get there. So in the next study, if I had the opportunity, I would only sample the 4th site to determine, the fraction of the smaller particles at the 4th site or at number 4, because I would be interested to find out exactly how much dust these people are exposed to around the office block. But this was a thesis for my master's at the time, and I was only happy to pass and move on and become a doctor again after such an intense study. I don't know if that answers your question, Doc, and thank you very much for such an interesting question. All right, colleagues, if there are no further questions, I would like to thank you for joining us tonight. This is a session that would have been on the 30th of October. Remember my issue on the day I had come back from ophthalmologist consultation with blurry eyes. I was not aware that my pupils were going to be dilated, so I couldn't read at the time. But I'm happy that I'm well now, and I was able to present this study. Better late than never. However, we are still going to have our regular monthly session on the 27th of November. In this case, we will be discussing an ethics subject, ethics in occupational health. And I've asked colleagues to share some of the ethical dilemmas that they have faced, because I'm trying for us to deal with as many ethical issues as possible, in addition to a brief presentation that I'm going to make on the day. On that note, colleagues, I would like to say enjoy your evening until we meet again this Saturday for the second part of the risk assessment webinar refresher. And again, we'll meet on the 27th at 6 p.m. For our last webinar of the year. Thank you very much, colleagues, and good night.
Thank you, Doc. Goodbye.
Thank you, Naka. Bye.
Thank you.
Thank you, Doc. Good night.